Hi, I'm Junyi Liu, and I'm a postdoc at Quicks and University of Maryland, and I'm going to introduce our ongoing work, RISC-Q, a generator for real-time quantum control system on chip that is compatible with RISC-V, or in other words, it's a design tool for quantum controller. So let's start with the real-time control in quantum computing. So in practice, we use a digital controller to control the quantum system. So that's what we call a quantum controller. And we use this controller to send control poles and decode the readout signals. So this and we will perform feedback according to the decoding result in a very short time. So that's why we call it real time. And this process has application in a lot of domains, like error correction, dynamic circuits, reconfiguration, calibration, and our topic, analog computing beyond the gate model. So let's take a look at the error correction. So in error correction, we first generate the measurement poles, and we decode the readout signal from the quantum system. We extract the error syndrome using the controller, and we send the correcting poles according to the syndrome as soon as possible, since we have very limited system life. So what's the difficulty in this system? For example, say we are doing a single qubit gate in the superconducting system, and typically we are sending poles in this formula. So the E is the envelope of the poles, and the omega is the frequency of the carrier, which is around 5 gigahertz for the current system. And said if we are controlling a single qubit, in practice, we will feed the digital analog converter in the controller like 8 billion data per second, and each data contains 14 bits. So basically, we need to generate 112 billion bits of data to control a single qubit. And if we want to control multiple qubits at the same time, we will need multiple times of data. So that's not an easy task. Okay. So in addition, we have other real-time requirements for the quantum control system. For example, we need very precise timing, because error in time will transfer to error in the phase of the carrier if we use direct digital synthesis. And we may need very low latency because superconducting system has very limited lifetime. And we know that the real-time control system based on software on a typical processor cannot meet all these requirements. And we really need a customized hardware to perform all this control. And actually, we have some example that meet this control. For example, Arctic, Cubic, and Kik are the open source ones, and below are the commercial ones that are used in the real-time control of quantum system. And let's remind where we are. So typically, users write their program using like high-level language like cubic and bracket, and their program will be compiled to hardware primitives. For the current RISC device, it will be Hamiltonian, and once we have fault-tolerant computer, we may use circuit as the hardware primitive, and the hardware primitive will be compiled to the real control instruction that are used by the quantum controller. So those instructions include the classical instruction that are used for arithmetic operation, branch, and memory operation. And we also have the quantum instructions that are used to send poles and for error correction. So the quantum controller will generate analog signal according to the instruction, so that we get the controlling voltage or current. So the current practice in the open source community is that people are using what we call a radio frequency system on chip, or RF SoC, to implement this control system. So we have a normal processor, an FPGA chip, and several high-performance DAC, ADC on that RF SoC. And according to the practice, we know that carefully designed FPGA controller on the RF SoC can meet the requirements. So we have example like Cubic and Kick. They all meet those requirements. However, so this solution is relatively cheap. So we know that an RF SoC with 16 DACs and ADCs cost around 16,000, and we can use 16 DAC to control at most 16 qubits at the same time. So we can spend as low as possible, like $1,000 to control a single qubit using this solution. So it's relatively affordable. But however, we will find that hardware design is complicated. We will introduce this later. So the goal of our tool is that we want to do fast prototyping of quantum controller. And we want the tool to be open source and high level. So more specifically, the reason that we need it to be open source and high level is because that we want to implement things similar to Cubic and Kick, and maybe with more functions, but using less human effort to implement. So we will explain why we need open source and high level for this purpose later. But first, we will take a look at the structure of a quantum control system to see the complexity behind it. So the most basic function of a quantum controller is to generate poles. And we will have a control unit that specifies which poles will be sent. For example, the control unit will tell the pulse generator, so please generate a pulse starting at time t with the following parameters. And the pulse generator will generate a binary encoding of discrete sampling of the amplitude. And DAC will transform this binary encoding to the analog signal. And to perform measurement and feedback control, we will need a decoder that decodes the readout signal from the ADC. And to operate this system, we may need a communication module so that we can load and store data from our personal computer. And we will find that there are numerous choices in the design of each component. For example, for the control unit, we can choose to use the general purpose CPU, or we can use the simpler finite state machine. And for the pulse generator, we have different strategies for the pulse mixing, the pulse compression, and memory allocation. And for the decoder, we can use traditional digital signal processing algorithms, or we can use a machine learning one. And for faster feedback, we may add some direct connection from the decoder to the pulse generator. And in AMO system, we may need to connect a camera to the control system. And we also have different choices on the protocol of the communication module. So, and as the system scales, we may need to connect multiple devices to control more and more qubits. So I think we have seen the complexity behind this control system. And we also see that there are a huge design space to explore. So we don't know which design is the best. We need to try a lot of designs and their combinations. So why do we need open source? Because we have very limited human power for developing the quantum control stack. So we not only have the components, all these components in the quantum controller, we also need to implement a whole software stack for this quantum controller, including the driver, the compiler, the libraries, and the test bench to check if everything is right. Okay. So we really want to collaboration instead of reinventing everything, reinventing all the wells. So we want an open source framework and everybody can collaborate. And why do we need a high-level tool? So because as we've seen, we need a lot of hardware customizability. We know that different experiments need different hardware designs, including like different functions. We know that different error correction protocol requires different decoder, and maybe different systems require different post generators. And we also need different parameters for different tasks. For example, different frequency, throughput, power consumption, or the area of the hardware design. So we really need a fast prototyping platform to explore the huge design space. That's why we need a high-level tool so that we can perform the fast prototyping. And we have the design space of different components and also the combination of the different designs. Okay, so let's take Linux as an example. In Linux, people collaborate on an extensible ecosystem, including the Linux kernel, the compiler, and the C library, so that we can save a lot of manpower. We don't need to reinvent those things. And for specific applications, Linux provides configurable and composable modules, including drivers, file systems, libraries, and applications. Those things are designed on a very high-level abstraction of hardware, so that we can obtain configurability and modularity. And people can do very fast prototyping of software in Linux because of the high-level and open source design. So let's imagine an ideal situation of our quantum control system. Maybe like Alice has designed a new decoder, and Bob has built a new post generator, and Charlie can easily integrate their design into his system to obtain the best performance. And to achieve this, it will be better that everyone shares the same instruction set. So we can notice that classical instructions are similar across all CPU. So we have arithmetic instruction, we have branch instruction, and we have memory operations. So if everyone uses the same instruction set, we can share a lot of software, including compilers, libraries, simulators, and test benches. So do we have some good candidates for such an instruction set? And we will say yes, we have RISC-V, and we will choose a RISC-V CPU as the control unit in the control system. So RISC-V is an open source instruction set that requires no licensing fee and has numerous open source reference implementations. So we can learn from those reference implementations and we don't have start from the ground. And RISC-V is extensible so that we can add instructions required by the quantum real-time control. And more important, RISC-V has a very great ecosystem, including some major compilers, simulators, and libraries, so that we can build our software stack based on this successful practice. And we can extend RISC-V with quantum instructions. For example, we have an instruction for sending a pulse. Like this instruction will contain all the parameters of the pulse, and the pulse generator can generate a pulse according to the instruction. So in addition to RISC-V, we also need a high-level hardware description languages. So the current control system like Cubic and Kick, they are written in Verilog and VHDL, which are low-level HDLs. So in this HDL, we need to manually write down every wires, registers, and all the connections in the control circuit. For example, if we want to implement a XC bus, so that's an interface used to communication with our personal computer. We need to handle 30 or 40 signals to establish a single connection. And that's very labor intensive. So instead, we will choose a high-level HDL, spinal HDL. So instead of writing a circuit, in high-level HDL, we write a program that generates the circuit. So to generate the interface on the right, we only need a couple of lines in spinal HDL, and we can obtain much better configurability because we can just modify a couple of parameters to change the design. So this enables fast prototyping in the design of quantum controller. And we'll look at some simple examples using the spinal HDL. So the first example is bus connection. Bus is a common approach to transfer data. And say if we want to record the readout data from the ADC, we may want to add a readout buffer to store those data, and we want to access this buffer through our PC. So we may need to add new bus connection to access this buffer. And we know that setting up a bus connection could be very tedious because we have a lot of signals to handle. By using a high-level hardware description language like spinal HDL, we can implement this connection with a couple of lines, maybe 2 or 3, to handle 30 signals. So it's much more efficient than Verilog or VHDL. And for modularity, we use the design pattern proposed in VEX RISC-V, which is a reference implementation of RISC-V. In this design pattern, every function of the processor or the control unit is implemented by a plugin. And adding a function can be done in a single file, so we don't have the coupling problem in regular hardware design. So if we are using Verilog or VHDL, adding some new function may need to modify the original framework and a lot of files. By using a more high-level or advanced framework, we can add new function by a single file. It's much more modular and better for collaboration. So we can have better collaboration and fast prototyping using this high-level description language. So let's summarize what we want to deliver. So first, quantum controller requires customized hardware because we need very high capacity of data processing. And second, we need open source for the collaboration in this community because we don't want to reinvent everything in every group. We don't have that human power. And next, we need high-level design tool to enable fast prototyping because we know that there is a very huge design space for the quantum controller, and we really need to explore it very fast. And we are building RISC-Q to enable this kind of collaborative development of quantum controller. And with the help of this framework, we are able to reproduce a controller similar to Cubic in around a month. So we can develop new things very fast using a high-level framework. And there are also some ongoing work. So we will experiment our hardware soon on the Cubic hardware. And we will implement some software stack for RISC-V with quantum extension, including compiler, simulator, libraries, test bench. And since we know that there are a lot of people using Kik, we may reproduce Kik later. And more important, we want to implement more interesting hardware designs for tasks like fast calibration, decoding, or reconfiguration. And hope that we can achieve this ideal situation soon. So, thank you.
All right, can I take questions? Please.
Okay, so when you talk about not wanting to reinvent the wheel, for a lot of the things that you discussed, Kik and now KikDog can achieve pretty much everything that you described, from the end-to-end process of high-level RGB waveform generation, pulse segmentation that then goes into the FPGA blocks that it has, and then the output registers. The ZCU you had up there is the ZCU 216, but also works with the ZCU 111. So why did you not choose to add upon Kik? Was it purely for the high-level interface?
So the first thing is that like Cubic and Kik, they all invent their own instruction set, and we think that's not a great choice because we have like major classical instruction set like RISC-V, and we have a lot of people maintaining this ecosystem. So for Kik and Cubic, they need to maintain their own like the software stack with like less than 10 people maybe. So I think it's better to choose a well-established instruction set instead of invent a new instruction set. And the second problem of Cubic and Kik is that it's very hard to modify the hardware design. So since they are using low-level design tools, and I think we don't know what's the best design for a specific task yet. We need to explore all the possibility in the hardware design. So we really need a tool to fast prototyping different designs.
But a follow-up to that would be that if you open up any of the Kik VHDL files, for example, look at the block diagram.
Yeah.
For some of the problems that we have to solve on quantum setups, you need that customizability where you go page by page, register by register, this flag, for example, if you're implementing a counter. These are for color center setups, not superconducting, but you lose that when you go to this high-level implementation side, no?
No, we won't lose that. So we can as we said, we can reproduce Kik because we can add customized instructions. So it's very simple.
But aren't you just reinventing the wheel there? Isn't that my question? Because they already have the ability to do this.
Yeah, so I think the potential of our framework is that we can do things more than Kik and Cubic. Yeah. So, and we can also reproduce them. Yeah. Okay. Oh.
Yeah. Right. Thank you. And let's thank our speaker again. Oh.